Happy day everyone. The today topic is complex analysis. A complex numbers Z is of the form x plus iy where x and y are real numbers and I is an imaginary unit with the property I square equal to -1. So you have a real axis, x is denoted as a real axis, y as the imaginary axis. X is the real part of z. So z is nothing but x plus iy. So x is equal to real part of z and y with the iota. So y is the imaginary of the z. Next comes the complex plane. Complex plane is the plane of complex number. So if you define in the unit sphere, so vector spanned by the vector 1 and I is the imaginary number. So every complex number corresponds to a unique point in the complex plane. So suppose if your example 1 plus I. So 1 plus I is a unique point in that complex plane. So the complex plane is sometimes called as a Argand plane or the Gauss plane. Similarly, the plot of complex numbers in the plane sometimes called the Argand diagram. Now we come to the extended complex plane. The function w equal to 1 by z defines a one-to-one mapping of the complex plane and to itself with two notable exceptions. The point z equal to 0 has no image and the point w equal to 0 has no pre-image. It's not, because if it substitutes z equal to 0, 1 by 0 gives you the infinity. So to rectify this, we extend this complex plane by adding a symbol called as infinity, called the point of infinity. So the complex plane together the union of the infinity is called as the extended complex plane. Next is a function of a complex variable. Usually the letters z and w are denoted by the function of the complex variable. So z is nothing but x plus iy. Similarly, w is a complex variable in the w plane, which is w equal to u plus iv. So the complex valued function. So function of a complex variable is usually denoted by w equal to f of z. Okay, so w is nothing but u plus iv, which is equal to f of z, f of x plus iy. So x plus iy, so u plus iy is the image of x plus iy. Now we discuss some function and the region defined in that. So the function w equal to iz plus 3. So this iz plus 3 is defined because w equal to whatever values of z, right, the w is defined. So w equal to iz plus 3 is defined on the entire complex plane. It's defined for all values of z, right. But w equal to 1 by z square plus 1. W equal to 1 by z square plus 1 is defined at all points except z equal to plus or minus I. If we substitute plus or minus I, 1 z square I square will be equal to -1. So -1 plus 1 will be equal to 0. So 1 by 0 will be infinity. So the exception case, the exception points are z equal to plus or minus I. Next is the w equal to mod z, but this is a real valued function of the complex variable because w equal to mod z is nothing but root of x square plus y square. So there is no imaginary part. So this is a real valued function of the complex variable z. Now we define the polynomial z. Suppose a0, a1, etc., an are the complex constants, right? Then the function p of z equal to a0 plus a1z plus a2z square plus etc. an z power n is defined entire in the complex plane. So there is no exception points, not defined in the exception points means we can't say it's a polynomial function. But so it's each and every point is defined in the entire complex plane is called as the polynomial in z. So generally we write the complex function as we discussed earlier, w equal to f of z. So f of z is, I already explained what is f of z. F of z is u of x comma y plus iv of x comma y, where u and v are real valued functions of numbers x and y. Now so we will see some examples. Now we are going to find the real and imaginary part of the function. Find u of x comma y and v of x comma y for the complex function. So f of z equal to z cube. So we as mentioned earlier, what is z? We know z is equal to x plus iy. F of z. So f of z is nothing but z cube. So z in place of z we replace x plus iy the whole cube. So x plus iy the whole cube is nothing but a plus b the whole cube. So we all know the formula for a plus b the whole cube. So expand using the a plus b the whole cube formula, and also we know that I square equal to minus 1. So I square equal to minus 1, we substitute here, you will get x cube minus 3xy square plus I into 3x square y minus y cube. So we know now z cube has been separated into real and imaginary. So what is the real part? Without the iota, that's called as a real part. So real part of z is x cube minus 3xy square. So and y, what is I into, so I is the imaginary part. So it's u plus iv. So this is of the form w equal to f of z is equal to u plus iv, where u equal to x cube minus 3xy square and v equal to v of x comma y. So u means u of x comma y. U is also represented in terms of your x and y, and similarly v also represented in terms of x and y. So v of x comma y equal to 3x square y minus y cube. Now we come to the limit. So limit so similar to the limit of a real number system, we can define the limit of a complex number system, and L is said to be the limit of f of z, right? So f of z usually is defined in the w plane as z approaches z naught. So limit z tends to z naught of f of z is equal to L. So how this we are going to see. What's the definition? So if for every epsilon greater than 0. So we all know what is epsilon. Epsilon is a positive quantity greater than 0, which is less than 1. So greater than 0, there exists a delta greater than 0. Then modulus of f of z minus L is less than epsilon. So modulus of f of z minus L is less than epsilon whenever modulus of z minus z naught is less than delta. So this limit, the function has the limit L only if, when it has the limit, only if the modulus of z approaches z naught. That is the difference between. So what is the distance between? The distance between z and z naught should be less than delta. So if it is true, then we can say the function has the limit. That is limit z tends to z naught, f of z equal to L. Now, based on the definitions, we have the theorem on the limits. Suppose limit, we have the two functions f and g. So, the f and g are the two complex functions, f of z defined by if limit z tends to z naught, f of z equal to L, and limit z tends to z naught, g of z equal to m. Then, these are the theorems, these are the results we can prove. So what are the results? The c into f of z, that is a constant into f of z equal to c into L. So the constant, suppose 2 into x plus iy is nothing but, so suppose the function approaches the limit, right? So it has a limit, then it will be the constant is multiplied with the function, then limit has the value 2 times of that. So c into f of z, which is equal to cl, where c is a complex constant. Next, addition and subtraction of the limit, right? So addition means f of z plus minus g of z, g of z is equal to L plus or minus m. Next, the product of the function. The product of the function is limit z tends to z naught, f of z into g of z, which is equal to L into m. Similarly, you can prove the L by m. Next comes the continuous. A complex function f of z is continuous. So what is the difference between the limit and the continuous? So the continuous function has the limit and it also defined at the point. So f of z naught equal to f of z naught. Limit z tends to z naught, f of z should be equal to f of z naught. So a complex function f of z is continuous at z naught belongs to c. Since it's a complex valued function, we are defining on the complex plane, we will write as a z naught. Z naught is a point, it belongs to C. Then for any epsilon greater than 0, we can find a delta greater than 0 such that modulus of z minus z naught less than delta implies modulus of f of z minus f of z naught less than epsilon. Next comes the differentiability. Right. So differentiability, let f is a function from the set A to the C to C function. The function f is a complex differentiable at a point z0 if the derivative of f of z is defined as the limit of the difference quotient. That is f dash of z can be defined as limit h tends to 0 f of z plus h minus f of z divided by h exists in C. Now we'll see the examples of the differentiability. The function f of z equal to z square is differentiable at every point and f dash of z equal to 2z. So we know the definition of the differentiability. By the definition we have limit h tends to 0 f of z plus h minus f of z divided by h. Right. So f of z plus h minus f of z divided by h. So what is f of z plus h? We have defined in the function f of z equal to z square. So z plus h the whole square minus z square. So it's of the form a plus b the whole square minus a square. So it cancel, you will get 2z plus h. Now approaches the limit. So when h tends to 0, we do limit h tends to 0, 2z plus h is equal to 0 will get equal to 2z. We have proved the result. Next is the example 2. We have f of z equal to z bar is nowhere differentiable because limit f of z similar to the previous example, it is z plus h the whole bar minus z bar. So by the modulus property I can write z plus h bar, h the whole bar will be z bar plus h bar minus z bar get cancelled, but h bar by h limit tends to 0 because it becomes infinity. Limit h tends to 0. It's not defined. If it is not defined, it's nowhere differentiable. Now theorems on differentiability. So these similar to the limits, we have the theorems on the differentiability. So if f of z is a complex differentiable, then see f of z equal to f of z the whole derivative equal to c into f dash of z. So similar to the limit, we have f of z plus z of z the whole dash, that is the whole dash is nothing but the derivative differentiability. We can write as f dash of z plus z f dash. Similar to the limits, we have product and the quotient rule and the chain rule. Now we come to the important theorem. This is a Cauchy-Riemann equations. So the Cauchy-Riemann equations are the necessary condition for the function to be a differentiability. So it's not the sufficient condition, it's only the necessary condition for the differentiable function, right, differentiability. So what are the theorem? The theorem is nothing but we defined f of z equal to u plus iv in the complex plane, right? And we know the differentiability by the definition of the differentiability f dash of z equal to, instead of h I have used the t, limit t tends to 0, f of z plus t minus f of z divided by t. So the both are same, the ux. So I can replace t by it, then this also limit t tends to 0, f of z plus it minus f of z divided by it. So but t is a real number. Now, if we are applying what is z plus t, we know what is z plus h. So we are applying in terms of u and v. So u of x plus t comma y plus iv of x plus t comma y minus u of x comma y minus iv of x comma y, which is equal to. So the second one will be equal to. Now the derivative will bring the u of x y towards. So we get the equation of, so dou u by dou x plus I dou v by dou x. Similarly, the derivative on along the vertical line. The first one is along the horizontal axis, the second one along the vertical axis. You will get the second equation as minus I dou u by dou y plus dou v by dou y. So the left hand side both are same, so we can equate the right hand side. So we equate the real part on the right hand side, we get ux and vy, similarly uy and vx. So equating this, we'll get dou u by dou x, ux equal to vy and dou v by dou x, that is denoted by v suffix x equal to minus dou u by dou y. So moreover, you substitute that, we get the differentiable equation. So f dash of z equal to dou u by dou x plus I dou v by dou x, which is equal to dou v by dou y minus I dou u by dou y. Now we verify the CR equations. So CR equation, we need to prove this, ux equal to vy and uy equal to minus vx. So CR equation, our function is f of z equal to z. So f of z will be denoted as u plus iy, which is equal to x plus iy. So what is equating real part? U equal to x, v equal to y. So differentiate with respect to x, ux equal to 1. With respect to x, here v, there is no x terms in the v, so it's 0. Similarly uy and vy. So compare CR equations are satisfied. So next example, e power z, e power x cos y plus I e power x sin y. Similarly, you can take what is u, what is v, and we can find out the differential partial derivative with respect to x and with respect to y. So dou u by dou x and dou u by dou y. So CR equation is also satisfied for the example 2. So the Cauchy, what we already discussed is the Cauchy-Riemann equations provides only the necessary condition of differentiability at a point. Okay. Next, CR equations are not satisfied for a complex function at any point. Then we can conclude that the function is nowhere differentiable. So for example, we have taken this, consider the function f of z equal to z bar. Okay. So ux equal to x and this is minus y. So ux is not equal to vy. The CR equations are not satisfied at any point. So we can say the function f of z is nowhere differentiable. Then CR equations are not a sufficient condition for differentiability. We have taken one example. We have xy by x square plus y square. Similarly, let's find out at the point z equal to 0. So you have taken the point z equal to 0, 0 comma 0. So this provides that Cauchy-Riemann equations are satisfied. Now we are going to prove, although the Cauchy-Riemann equations are satisfied, but the function is not differentiable. So we take a path y equal to mx and we substitute and we cancel. So numerator we can take x square common, denominator also x square common, we can cancel that, we get f of z equal to m by 1 plus m square. Now as z approaches the 0 along the path y equal to mx, the whole function depend on the m by 1 plus m square. So for each values of m, we'll get that each values of f of z. So it's not unique. So f of z does not have a limit. So the limit is not exist. So f of z is not even continuous and f of z is not differentiable at z equal to 0. So this is an example. We can say that the function is not continuous, but CR equations is satisfied and it's not differentiable. Now important theorem, this is a sufficient condition for differentiability. So if we prove this then we can say that the function, the complex valued function is differentiable. So what is the statement? F of z equal to u of xy, you all know we express f of x into u of xy plus iv of xy and CR equations are satisfied. We are going to prove the function is differentiable. So u of xy exists by the mean value theorem. For function of two variables, we can write these two results. What are the two results? U of x plus h1 comma y plus h2. This left hand side equal to. So when I can write only by the mean value theorem. So h1 ux of x comma y plus h2 uy of x comma y plus h1 epsilon 1 plus h2 epsilon 1. So this function epsilon and epsilon 2 we always know that it's a greater than 0, but when it is 0, when it approaches 0, when as h1 and h2 tends to 0. Similarly, the second equation v of x plus h1 comma y plus h2 minus v of x comma y. So right hand side similarly we have taken as epsilon 3 and epsilon 4. So epsilon 3 and epsilon 4 tends to 0 when h1 and h2 tends to 0. So f of z plus h minus f of z, we all know from the definition what is f of z plus h minus f of z. Mean value theorem, we can substitute the right hand side in place of u of x plus h1 and y plus h2. Substitute and you can bring to the h1 and h2 together. So you will get h1 plus IH2 is nothing but h. So you replace and use the CR equation. You will get the equation of ux of x comma y minus iuy of x comma y and this h1 by h. So we all know that h1 by h modulus of this value will be less than or equal to 1. If it is less than or equal to 1 and it approaches 0, so h tends to 0. So we have proved that limit h tends to 0, f of z plus h minus f of z divided by h equal to ux of x comma y minus iuy of x comma y. So we have proved this. So left hand side is nothing but limit h tends to 0, that's a differentiability. Right hand side we have proved this ux of x comma y minus iuy of x comma y. Then we can say the function is differentiable. So this is the necessary and sufficient condition for the differentiability. Thank you.